Good evening, everyone. Welcome to the first live session for the course Concrete Technology offered by NPTEL. I am Harshit Agrawal, a PMRF PhD scholar from the Department of Civil Engineering, IIT Bombay, and I will be conducting weekly live session for this course for the entire course duration. So first of all, what are these doubt clearing and interactive sessions all about? So these are weekly sessions that will be held every Friday from 6 p.m. to 8 p.m. till the course runs. And how we will interact in these sessions. So we will interact either by answering to the questions that I will ask in the chat box, by posting your questions in the chat box, or by raising hand, unmuting and speaking, asking your queries. Apart from the class, you can always use the discussion forum of the course where the questions you can post and those questions will be addressed through the discussion forum itself or in the next live session. And attending these sessions regularly will help you to answer the graded assignments easily, and it will help you to further understand complex topics holistically. So in today's session, we'll first have an overview of the course just to familiarize everyone what is this course will be offering to the learners. Then we will see the course outline, that is how the course is divided into 12 weeks of content, and then we'll start with the week 1 where we will first have a recap of basics of concrete as a construction material, where we talked about components of concrete and concrete as a composite material. Then we'll start the main discussion part wherein we will go deep into cement as a binding element of concrete, its production, its composition, microstructure, hydration and hydration kinetics, and the presence of water and pores in a cement paste assembly. So the theoretical part that we will be discussing today, it would be just a quick recap of the week's content that you have already seen, where if anyone has any doubt, they can ask their queries. Along with the theory, in between I will introduce you with several questions to challenge your understanding about the subject. So around there will be around 14 to 15 questions that we'll discuss today, and at the end I will make myself available to solve any other queries related to the assignment questions or regarding the content. Okay, so I hope everyone are clear with the flow of this session. I just advise everyone to attend the sessions regularly so that it will help you to have a thorough understanding of the course. And whenever anyone has any doubt, just type in the chat box or unmute and speak. In between, when I will pause for discussing questions, I will have a look at the chat box and we will discuss the queries. So in this course
In this course,
uh, in this course we have five basic elements of concrete technology that will be covered.
that will
Just a second, my voice is repeating. Okay. We have five basic elements of concrete technology that will be covered. So first is materials and properties, in which we'll cover the basic materials used in concrete, including cement, aggregate, water, and admixture, and I will explain you their roles and properties. Then second, we'll talk about mixture design and proportioning, which teaches the principle of concrete mixture design, focusing on achieving desired strength and durability through proper mixture proportioning. Third will be about production and quality control, which talks about processes of mixing, placement, and curing of concrete to aid the quality control. Fourth part will be special purpose concreting, which will explore various types of special concretes like high performance concrete, self compacting concrete, and fiber reinforced concrete. And finally, fifth will be durability and sustainability, which addresses factors affecting concrete durability, mainly corrosion, and introduces sustainable practice in concrete production. Okay, so it's a 12-week course starting from week 1, where we'll first have an overview of concrete and cement based on its production and composition, and we'll end with week 12 where we'll discuss about special concrete and sustainability in concrete production. Okay, so the course is divided into 12-week content. Week 1 is basics of concrete and cement. Week 2 will go on properties and testing of cement. Then week 3 will be about aggregates and chemical admixture. Week 4 will be about mineral admixture. Week 5 and 6 will be about mixture design of concrete. Then in week 7, we'll come into the production and quality control. Week 8, we'll talk about mechanical properties of concrete. 9 will be about durability properties of concrete related to creep and shrinkage. Then in week 10, we'll talk about rebar corrosion. Week 11 will come to special purpose concreting, mainly high strength concrete and self compacting concrete. And in week 12, we'll talk about fiber and roller compacted concrete, and we'll talk a little bit on the sustainability point of concrete. Okay, so let's start with the week one. Okay, so we all are well versed with the fact that in the present world, concrete is the most widely used construction material. Okay, and there are facts which supports this statement. So fact one is it is the second most consumed material on earth after water, and fact two is more than 5 million tons of concrete is consumed every year. Now, what makes concrete such so special? Why it is used so much? It is because of its five key characteristics, which makes concrete a very most widely used material. First is the behavior. Concrete can act as a barrier. It has an excellent water resistance property. Second is strength. Concrete can withstand load. Okay, it can have very high compressive strength, which can withstand any loading action. Third is affordability. It is easily available. All the raw materials that we use for making concrete, they are very easily available, and it is cheaper compared to steel. Okay. Fourth, durability. It has high lifespan. So any structure that is made with concrete, it has a very good life cycle. Okay. And fifth, flexibility. So we can mold concrete into any desired shape and size, whatever we want. Okay. So these five key properties, they make concrete a such commonly consumed material. Okay. Now, when we talk about concrete, how we are defining concrete, like what is concrete? Okay, so concrete is nothing but an artificial stone-like mass that you can say, which is composed of, which is made by mixing several materials, which are binding materials along with aggregates, water, admixture in a specific proportion. Okay, so when these materials are mixed together in a fixed proportion, we get a stone-like mass, and this stone-like mass is what is known as concrete. Okay, so if we write this in terms of a formula, so we can say concrete is equal to a binding material plus water plus fine and coarse aggregate plus admixture, which is an optional entity. Okay, so in a layman term, if I say concrete is a material which appears to be a flowable slurry kind of thing in the start, but over time it will harden and set into a definite stone like mass, okay, which can resist any kind of loading action as per requirement. Okay, so this is how we can define concrete. Now, if we see different components of concrete, each component like the binding material, water, aggregates and admixture, each component has a very specific role in concreting, and that's why studying each component separately is important to understand the composite action of concrete. Okay, so if we just start with this equation of concrete as a mixture of binding material, water, aggregate and admixture. In this, the binding material is the main element of concrete mixture, and this gives us the strength that we need from concrete, and it binds all the ingredients of concrete together into a specific shape. And the most commonly used binding material is cement. Okay, now this binding material, how it gives the strength to concrete, it reacts with water, which contributes in reacting with the binder as well. It provides the workability to make a paste which hardens over time, which gives us this stone like substance called concrete. Now, apart from binding material in water, we have aggregates in concrete, which are inert material. So we use sand as fine aggregate, and we use crushed stones or gravels as coarse aggregates. And what is the role of aggregate in concrete? They provide the dimensional stability to concrete. Why we are calling it dimensional stability? Over time we'll understand these things, like why, what is the need of aggregate, why we are using aggregate, why not just cement and water, using cement and water we can make concrete. So over time you will understand the need of each of these components. Okay, then there is additional component which are known as admixtures, which are optional. So there are chemical and mineral admixture that are also added as a part or as a replacement of these materials, and they are used to enhance the performance or durability of concrete. Okay, so based on the type of concrete we want, the strength of concrete, the durability of concrete, or the need, the purpose of concrete, we can adjust the proportions of these uh, raw materials to get the final concrete product that we want. Okay, so all of these components, they combine together to make a stone like substance which is known as concrete. Now, based on the proportioning of various ingredients used in concreting and the admixture content, we can classify concrete into different types. There is regular concrete, which is also known as plain concrete. Then there is reinforced concrete, there is high strength concrete, high performance concrete, self consolidating concrete, vacuum concrete, shotcrete, compacted concrete, glass concrete, asphalt concrete, rapid strength concrete, polymer concrete. And right now, as per the list, there are can be 23 different types of concrete which are listed. Okay. Among these listed concrete, the most commonly used concrete is the reinforced concrete. Okay, so as we'll progress in the course, we'll understand that concrete is a brittle material. Okay, it has high compressive strength, but it has very low tensile strength. Now, in actual application, when we'll talk about the loading that is acting on the structure, there are both compressive and bending or tension loads that act on the structure. So, since concrete is weak in tension, we need some element that is inside concrete which can take the tensile load, and that's why we embed steel reinforcement inside concrete. So concrete takes the compressive load, steel reinforcement takes the tension load, and they both combine to make a composite material which is used in construction purposes. Okay, so this is just one type of concrete. Apart from this, there can be different types of concrete. So when we'll understand each of the components of concrete and what is the mixture proportioning, what how do we judge the mechanical property, durability property, then we'll have an understanding about, okay, how we can engineer the concrete for our purpose. So, before moving deeper into different types of concrete, we must understand the role of each component of concrete. And among these various components of concrete, we'll start today discussing about the binding material, okay, which is the main element of concrete when we talk about all the raw materials that are used in concrete. Okay, so when we talk about binding materials, there are two main classifications of binding materials that are used in construction. There is lime and there is cement. Okay, so first we are talking about lime as a binding material. So if you know, lime has been used for building as a building material since thousands of years. Okay, dating back to Egyptian, Greeks, and Roman period. And in India, lime was a key ingredient for making mortar. If you have heard about the name surkhi, so surkhi mortar was commonly used in India in historical ages, where lime was combined with brick dust to enhance the performance, and with koa and stones to make, as where koa and stones was used as aggregates to make mortar. Okay, and all the ancient structures that you see around, like forts, temples, palaces, they are all built with lime mortars and plasters, and they were highly valued for their strength and durability. Okay, so you can see this is how this lime looks like, and it was combined with koa and stone in the presence of water and some brick dust to make surkhi mortar. And all these medieval structures that you see, they are all made of lime mortars. Okay, so when we so if we simply understand how lime was used as a binding material, we need to understand something which is known as lime cycle. Okay, so Lime as a binding material is produced through this lime cycle. Okay, where limestone, which is a sedimentary rock which is present naturally, it is heated up till 600 degrees Celsius to produce quicklime, which is known as CaO. Now, in this quicklime, when we add water, it converts into slaked lime, which is CaOH whole twice. And this slaked lime, it reacts with CO2, which is present in the atmosphere, to harden back into limestone, which gives us the definite structures that we want. Okay. Now, if we heat this limestone again, we'll form quicklime. So we can again produce lime, and this makes this cycle of lime durable, reusable, and eco-friendly in construction. Okay. Now, based on the source and the reactivity of lime, there are two categories of lime which are present. One is known as hydraulic lime, and one is known as non-hydraulic lime. So, can anyone tell me the difference between these two? What is hydraulic and what is non-hydraulic lime? And apart from this question, just think about these two extra questions also. Which of the following property is the weakness of lime? And what is one of the modern application of lime as a construction material? Just think about these three questions for discussion. And in the meantime, if you have any doubts, you can ask now. You will get the link. I'm recording the session. So once the session will be over, I will upload the session on YouTube, and the link will be shared to you by the end. So I am portal. The link and the presentation both they share. Just try to answer these questions for now. Can anyone tell me what is the difference between hydraulic lime and non-hydraulic lime? You can unmute and speak also, and you can type in the chat box also, whatever is comfortable for you.
So hydraulic lime is the one which sets with the reaction with water, whereas non-hydraulic doesn't require water to set.
Okay. Anyone else? How will non-hydraulic lime set then?
Basically, with carbon dioxide reaction with the carbon dioxide,
Okay.
air.
Anyone wants to add up on this? That will be shared to you. How to find link of this recorded videos? It will be shared to you by the SOAM portal on the course page. So this is the screen that you see now on SOAM portal. So there they will share the link of in this tab problem solving session and the recording. So here they will post the link. Okay, and if you will click here, you will get the sheet where all the links and the folder for the presentation will be there. Okay, so let's discuss the first question. The one who answered it was correct. So when we talk about hydraulic lime, so hydraulic lime is something where it sets just by reacting with water. Okay, it can set by carbonation also, but it sets also by reacting with water. How? Because it has certain impurities that are present in lime which can make lime react with water and form certain products which can gain strength over time. Okay, and this was something which was used as a basis for production of modern cement. Okay, so this hydraulic nature of lime gave the idea behind the production of making of modern cement. Okay, and then there is non-hydraulic lime. So as the name suggests, non-hydraulic lime is something which won't set just by reacting with water. It sets by only by reacting with CO2 in air and forming CaCO3. Okay, so this is the difference between hydraulic lime and non-hydraulic lime. Second question, which of the following properties is the weakness of lime as a binding material? Can anyone tell me? See, D will be the common answer for everything, for every kind of binder material. Weathering action is weakness for lime also, cement also. The one weakness that was discovered for lime, why lime was discontinued, why cement came. Why not we are using lime now also? Why what was the need to produce cement? Yes, the correct answer is strength. Okay, so when we talk about lime, it has lower compressive strength compared to modern binder materials like cement. Okay, that's why it is not suitable for heavy structural load activities. Okay, lime, it takes time also to gain strength. Okay, why it takes times? That we'll understand later on in this session only. Okay, it is the composition of lime which makes it slow in terms of strength gain. Okay, while cement, it can gain strength rapidly within a week. Okay, that is not possible with lime. Okay, third question, mention any one modern application of lime. So what is till now, now also we use lime. What is the use of lime? Even though it is not good in strength, why we are using lime now also? Mr. Binod, yes, this is the first video lecture for this subject. Okay, so there are lectures that are uploaded by the NPTEL team also on the Swayam portal. So that is the detailed lecture series. These sessions, they are quick summary of whatever you have discussed in those lectures. In addition to that, there will be questions that I have made by myself and I will be discussing. Okay, just focus on the theory part right now, that what we are discussing, all these general doubts, everyone can ask it at the end of the session. Okay, I'm getting answers at internal plastering. Okay, soil stabilization, no. As a polymer, no, it is not used as a polymer. So we can say lime, one modern application of lime is in the repair and restoration of old heritage structure. Okay, so heritage structure that we talk about, they were originally made with lime mortar. Okay, now for repair of those structures we need a material which is compatible to those that material that originally was used, and that's why for compatibility reason, with historic materials, we use lime uh, till date in for repair and restoration purpose. Okay, cement and lime both are very different from each other. We can't combine cement and lime in the same structure. They have different thermal expansion coefficient, they have different shrinkage properties, water permeability properties. So both of them are not compatible with each other. We need two materials which are close to each other, which can work together. Okay, that's why lime is used for restoration and repair purposes for ancient heritage structures. Everyone are clear with these three questions? Can we move ahead? Okay. Now, after lime, let's move on to cement as a binding material. Okay, so let's first explore the history of Portland cement, how Portland cement came. Okay, so the history of Portland cement, it is made of three key facts. Fact number one, Louis Joseph Vicat. So he was the person in the early 19th century, a scientist named Louis Joseph Vicat first prepared Portland cement by mixing limestone and clay, which laid the foundation of the modern cement that we are using. Okay, then in 1824, a scientist named Joseph Espedin, he patented this hydraulic cement. So first we have talked about hydraulic lime. From hydraulic lime, the idea of cement came, and then Joseph Espedin he patented this idea of hydraulic cement, which was termed as Portland cement later on. Okay, and why this name Portland came? Because it was the name Portland was chosen because the cement resembled the properties of a Portland stone, a type of limestone which is present in a region known as Dorset in UK. So in United Kingdom map, if you'll see, there is a region called Dorset, and in Dorset there is an area which is named as Portland. Okay, so from this area, the limestone that was present in this area, it resembled the property of the cement that Joseph Espedin he patented. Okay, so since it resembled the property of this Portland limestone, the cement was named as Portland cement. Okay, so this is how the name came, Portland cement. Okay, now in modern age, how we produce Portland cement? So in cement production there are five key stages. Okay, stage number one is the crushing of raw materials. Okay, so it all begins with crushing of raw materials like limestone and clay, along with some impurities of iron oxides. Okay, once they are crushed, they are stored in raw meal, which are like big storage bins you can see on cement production sites. Okay, then second step is grinding, proportioning, and blending of the raw meal. Okay, so the crushed material that we have stored, they are now grinded and blended in precise proportion. Okay, so these all raw meals, they are proportioned, okay, in specific quantity to create a homogeneous mixture. They are proportioned and then they are blended to create a homogeneous mixture. Okay, then third stage is preheating of raw meal. Okay, so once this mixture is proportioned, the mixture is preheated using hot gases in a preheated tower. Okay, and what is the need of these preheated tower? They just reduce the energy consumption in the next stage of cement production. Okay, so initially the material is just preheated before sending it to actual heater. Okay, so now the fourth stage is kiln phase. Okay, so this is the main phase of cement production. Okay, so the preheated material from stage 3, they are heated to a high temperature in this rotatory kiln. Okay, where all the chemical reaction takes place to form the final product, which is known as clinker. So what is happening inside this kiln phase? So you can see in this 4 point flow chart, there in different temperature ranges inside the kiln phase, there are different activities that is happening with this proportion raw meal. So at initially 100 degrees Celsius, evaporation of free water happens. Then from 100 to 430 degrees Celsius, dehydration and formation of oxides of silica, aluminium, and iron, it takes place. Then from 900 to 982 degrees Celsius, the CaCO3, it decomposes into CaO, releasing CO2. So we'll get CaO. And then at further higher temperature up till 1510 degrees Celsius, the cement clinker is formed, where CaO, it combines with silica, aluminium, and iron oxide to form different solid solution phases. Okay, and the end product that we get from this, it is known as clinker, cement clinker. Okay, once we get out of the kiln phase, the stage 5 is cooling and final grinding. So once we get the clinker from the rotatory kiln, it is cooled down, and then gypsum is added to the cooled clinker, and it is again grinded into fine powder, which is known as cement. Okay, which is stored in big containers known as silos, and it is dispatched for packing and production. Okay, so this is the entire cycle of production of cement, starting with crushing of raw materials, grinding, proportioning, preheating, kiln phase, and final cooling and final grinding. Okay, so this cooling phase is very important. Later on, we'll see what is the importance of this cooling phase through one question. Now, since we have talked about both cement and lime and how they are produced, just try to answer these two questions. What is the difference between hydraulic lime and cement? If anyone can answer. So hydraulic lime also reacts with water and sets. Cement also reacts with water and set. What is the difference between the two then? No, it is not like that. We need to heat lime to decompose it to again use it. It is not like if we add water again lime will decompose. Because CaCO3 is formed, na CaCO3 can't react with water, so we can't make it active again. Degree of setting, hmm, not the answer I am looking for. Hydraulic lime sets so slowly, whereas cement sets fast. Can you tell me the reason? Although we'll discuss this later on, but still. Yes, hydraulic lime has lower compressive strength than cement, but why? Both of these questions, set slowly, cement sets fast, higher compressive strength, they can have one very common answer. So if you have went through the lecture content, you may know a little bit about this. Okay, I can see like we are going very away from the actual answer. So let's stick to basic right now. Okay. By the end of this session, you will be clear with this question answer. Okay. So when we talk about hydraulic lime, we know it sets and hardens with water and CO2. CO2. Both can make a hydraulic lime set. Okay. Whereas when we talk about cement, it sets because of hydration reaction with water. That is the only source of hydration of cement setting. Okay. Now, one more point that is very important to understand hydraulic lime. How it is produced. Hydraulic lime is produced by heating limestone and clay till 700 to 800 degrees Celsius only. Whereas in cement, we are heating limestone clay and impurities till 1500 degrees Celsius. And this is very important. This is the point which makes limestone, hydraulic lime, and cement differ from each other. Because when we heat it till 700 to 800 degrees Celsius, the oxide composition that we are getting in hydraulic lime it is different, and the composition that we are getting in cement it is different. Okay, so I will just give a hint on this what it is. In limestone we get C2S as the major component, whereas in cement we make C3S also. Okay, and this C3S is responsible for early strength, whereas C2S is responsible for so slow strength gain. So that's why hydraulic lime has slower strength gain over time, whereas cement has faster strength gain initially also. So this point we'll see later on also. What is C2S, what is C3S and everything. But for now, just to answer this question, just remember this point. It is about the way hydraulic lime is produced and the way cement is produced. And third point, which was told by someone, hydraulic lime has lower strength compared to cement. Okay, so these three key points are there when we compare hydraulic lime and cement. Okay, and why? What is the reason behind this lower strength? Again, this composition C2S and C3S. Okay, so later on when we'll talk about hydration of cement, it will be clear to us. So just try to answer fifth question now. What is the source of CO2 emission in this clinker production? So when we talk about this production phase, from where the problem of CO2 emission is coming, like we talk a lot about replacing cement with certain sustainable material. what is the problem with clinker production which is making cement such hazardous material for nature? From where that CO2 emission is happening? What is the age of cement and any benefit of fresh 1 week old cement compared to older cement? Uh, Old cement will be carbonated initially, so it won't react with water that efficiently. Okay, and fresh cement, it is less. Like old cement, it will be hydrated, not carbonated, sorry, it will be hydrated. So what happens now, if we leave cement open in ground or open to atmosphere, it absorbs water from atmosphere and it hardens. Okay, once it has hardened, it won't give that ability to bind material together because it has already absorbed water and hardened. Okay, whereas if we take fresh cement, it is free from any kind of hardening or setting. Okay, so when we add it in concrete, the whole cement proportion that we have added, it will be available for reaction, it will be available for reacting with water. So that's why storage of cement becomes very important. Okay, and you can see over time a cement bag, it becomes very hard, like a stone like mass it becomes. Why? Because it has already reacted with water and formed hydration products. There are several ways in which you can judge just by looking at the cement bag whether it is good or bad. First is the hardness. It should not be like lump mass. Okay. Second is the color. Cement is generally grayish in color. If it is not grayish in color, it means that there are certain impurities that are present in the cement, which is not needed. And third is the when you touch cement, it should feel cool. Okay, if it is not feeling cool, it means that it has undergone some hydration, and because hydration is an exothermic reaction, you won't feel the cement to be cool. Okay, so these are the three ways in which generally, just by touching the cement or touching the cement bag, you can judge whether the cement is good or not. Okay, let's go back to this question. Yes, the correct answer is B. Decomposition of limestone, it releases CO2, and the burning of fuel in the kiln phase, which also releases CO2. And these two are the major problem that when we talk about what is the problem with cement production, why we are looking for replacement of cement, because of these two reasons. Okay, they are the major contributor to CO2 emission in the world right now. And to reduce the use of cement, we are going towards sustainable construction practices. Okay, now to understand the chemistry behind what we obtain from this kiln phase and what we called as clinker, we need to understand the oxide and the compound composition of Portland cement. Okay, so after passing through this kiln phase, limestone and clay, upon exposure to higher temperature, they form different oxides of calcium, silica, and aluminium. So limestone is the source for calcium, and clay is the source for silica and aluminium. Along with this, we also add some iron impurities in the initial raw mixing, which is the source for iron oxide. Okay, so these all limestone, clay, and impurities, upon exposure to high temperature, they convert into different oxides of calcium, silica, aluminium, and iron after liberating CO2 and water. Okay, so for Portland cement, the composition of oxide, like for general Portland cement that we get in market, the composition of oxides that are present in the clinker are of this order. So calcium oxide is around 60 to 67%, silica oxide is around 17 to 25%, alumina oxide is 3 to 8%, iron oxide is 0.5 to 6%, magnesium oxide is 0.5 to 4%. There are alkalis which are present, which is 0.3 to 1.5%, and there are sulfates also, SO3 also, which is present in the range of 2 to 3.5%. So this also act as a baseline for cement production. So initially, all the raw mixing proportioning that is done, it is done to make sure that the range of oxides that are present in the final cement, it should be in this range. Okay, and how we can determine the oxide composition of cement? So if we have a powdered Portland cement, there are several microstructure testing that we can do, and one of those testing is known as inductively coupled atomic emission spectroscopy. So this testing can give us the composition of cement. Okay. Now, when we further expose the cement to higher temperature, what happens? These oxides they blend and convert into solid solutions, okay, of different compounds. So the CaO it will blend with silica, aluminum, iron bearing phases into solid solutions. Okay, and these compounds that are obtained, different solid solutions or different compounds, they are which are obtained, they were first discovered by the scientist named Le Chatelier, which demonstrated in 1887 that clinker contains several different minerals or compounds. And later on, in 1897, these minerals and compounds they were given specific names like elite, belite, silite, and phyllite. Okay, so the proportion of these formed solid solutions of different compounds they are shown in this table. So we have tricalcium silicates where 3 moles of calcium oxide they combine with 1 mole of silica oxide. This is also known as C3A in abbreviation, and it is known as elite. It was given the name as elite. Then this dicalcium silicate, which is represented as C2S, which is known as belite. This tricalcium aluminate, where 3 moles of CO is present and 1 mole of Al2O3 is present, which is known as C3, which is abbreviated as C3S and is known as aluminate. Then this tricalcium alumina ferrite, which is represented as C4AF ferrite, and there is gypsum which is present, which the chemical formula for which is CaSO4.2H2, and it is represented by this CSH2 and underscore sign below S. Okay, and the proportion of these final solid solution in cement is in this range. Okay, 45 to 60% is C3S, 15 to 30% is C2S, 6 to 12% is C3A, 6 to 8% is C4AF, and approximately 4% or less than 4% is gypsum. Okay, and these composition, this is something which differs when we differ different types of cement, and this is the main part that we need to remember when we later talk about hydration of cement. Okay, so if we see the same thing of raw material and how it is changing with temperature in the kiln phase. So initially you can see we have limestone, we have quartz, we have silica, we have clay, alumina, we have iron oxides. Okay, they are heated till 600 degrees Celsius where only moisture loss is occurring, and then beyond 6 there will be some phase changes also which can occur, like quartz can convert into from beta phase to alpha phase, or there will be moisture loss from the system. Beyond 600 we'll see that calcium carbonate it will liberate CO2 and it will convert into CaO. Okay, and subsequently this belite and certain calcium alumina phases that will also start to form. Beyond beyond this 1200 degrees Celsius, you can see this belite phase C2S, it starts to convert into elite. Okay, and CaO it starts to blend with the quartz and clay to form belite. Okay, so these phase conversion they start to happen. So till now, till 1200 degree 900 degrees Celsius, what was happening? All the CO2 was liberated, silica oxide, alumina oxides, and CaO, they all formed. Now they have started blending into final solid solutions like elite, belite, calcium, aluminate, phyllite, all these phases they start to form. Okay, from beyond 900 degrees celsius till 1500 degrees celsius. And this is what I was telling you initially also when we talked about difference between hydraulic lime and Portland cement. So in hydraulic lime we are heating limestone only till 700 to 800 degrees celsius. So if you can see this line mark, up till 800 degrees celsius or even till 900 degrees celsius, you can see there is only C2S which is present in the system. Okay, whereas in cement there is this C2S also and there is this C3S also. So this is the change in the composition that happened from hydraulic lime to cement upon further heating of hydraulic lime. Okay, and that's why Portland cement show higher strength compared to hydraulic lime. Okay, now once the clinker is produced after this heating phase, there is one initial preliminary quality assessment of clinker that is done, and that quality assessment test is known as lime saturation factor. So what is this lime saturation factor? It governs the ratio between elite and belite, C3S to C2S ratio. Okay, and what this ratio factor tells, it shows whether the clinker is highly likely to contain an acceptable proportion of free lime or not. Okay, so what happens if there is excess of CaO present in the clinker? Okay, this CaO can give problem of soundness, okay, in cement. So in next week or next to next week when we'll talk about testing of cement, we'll see that soundness is one of the test that we do on cement, which defines whether the cement is expansive in nature or not. Okay, so to check whether the cement and the soundness issue, it comes in cement when there is high proportion of lime present in the cement, free lime present in the cement. Okay, so once the clinker is produced, we check this lime saturation factor in cement. Okay, and how it is checked? Based on the oxide composition of cement. So if we know the oxide composition of clinker that we have produced, using this formula we can calculate the lime saturation factor. And if this factor is more than 1, then we say that the clinker contained unacceptable proportion of free lime, and thus that batch of cement needs to be rejected. Okay, now before passing any material through that kiln phase, suppose we know the oxide composition of a raw meal. Now how we determine that, how we will proportion the raw meal for getting the final compound composition that we want. So for that we have an equation which is known as Bogue's equation. So if we know the oxide composition of cement, using these sets of four equation we can determine what will be the final compound composition in cement. Okay, so based on this we can do minor adjustment in the raw materials that we are mixing, so that we can have the adjustment in the final products that we are getting. Okay, so this is known as Bogue's equation, which relates the oxide composition into compound composition. Okay, so just give it a try. Okay, how to use this equation? So I have this question right now for you, where you need to determine the compound composition of the cement for the given oxide composition. So this is the oxide composition that I have given to you. Use these sets of equation and determine what will be the proportion of C3S, C2S, C3, and C4AF. Okay, and also check the lime saturation factor. What is the lime saturation factor? Is it greater than 1 or is it less than 1? So just do this calculation quickly, and in the meantime if you have any doubt in the discussion that we had till now, you can ask. Okay, I see multiple questions. You will get the this class content on Swam portal. Why does GK cement appear lighter? That may be due to some change in the composition, although it should not appear like that. Both are grayish in color. I haven't observed the change in color like in our laboratory that we use. The cement that we use, generally both are almost same in color. Maybe sometimes it is the thing that I have told you initially, due to hydration. If you keep the cement bag exposed in atmosphere, it may hydrate. Okay, that can also give a little change in the color of cement. Okay, or in the way the raw meals are proportion, it won't be exactly the same in both company. Okay, that can also give the difference. Exam format, I am not sure what it will be. I guess it will be objective types only, not theory. White cement and gray cement, we'll see later on, in week 2 or week 3 content, when we talk about different types of cement and cement proportioning. What is the difference between white cement and gray cement? So just wait for that session. Regarding heat of hydration, how significantly does fineness of cement impact the risk of thermal cracking? So right now, like just a few slides ahead, we'll talk about hydration of cement. So we'll see cement is a surface phenomena. Hydration starts from the surface. So finer is the cement, more is the surface area available for hydration to occur. So if more surface area is available for hydration to occur, there will be more exothermic reaction that is happening. So there will be higher will be the risk of thermal cracking. Okay. So if we use ultra fine cement for high strength, do we need special admixture to control the heat? Yeah, you may need to slow down the heat gain, the hydration rate. So generally there are set retarders, set accelerators, so that depends upon the need. Okay, so when we'll talk about admixtures that are used in concrete, this part will be covered. What is the role of fly ash and iron slag? Any change in manufacturing? Fly ash and slag, they are not produced. They are byproducts of other industry. Okay, so slag comes from steel industry. Fly ash comes from coal. Okay, so they are not produced like how we produce cement. And when you talk about PSC and PPC, here cement is there, fly ash is there, and both are mixed together and grinded. Okay, they are not added with the initial limestone clay and everything during cement production. Okay, so we'll see how fly ash and slag is produced. Okay, when we'll talk about that, it will be clear to you about PSC and PPC. Why tricalcium silicate release more heat? That is because of the structure, the atomic structure of tricalcium silicate. Okay, so this also will talk just few slides ahead. Okay, what, why certain phases are formed, why C3 is forming, C2s is forming, why CS is not forming, C1s is not there, C1.5s is not there, why only these two phases are there, why C3 is there, why C3 has more hydration rate, why it releases more heat. So all those things, it will be clear when you will see the atomic arrangement of calcium, alumina, silica, how they are arranged, how they are packed. Okay, from that you will get the clarity. 43 and 53, the difference is the how much strength they achieve at 28 days. Okay, so when we say about grade 43, it means that at 28 days the cement mortar, if we make cement mortar, it will achieve a strength of 43 MPa, and 53 will achieve 53 MPa. So the difference comes in the proportion again. The C3s content, the C2s content in the cement, they differ. Okay. Color depends upon iron oxide. So if you have more iron oxide than needed, then you will see color will slightly shift from dark gray to light gray. We'll discuss about components of cement. Okay, again based on the proportion variation comes. Did anyone do this calculation? Just I will mute myself for a minute and I will freeze on this slide. Just try to do this calculation. How can M43 cement help in achieve? It depends upon the water to cement ratio, the aggregate content. A lot of thing comes into action. Okay, using OPC 43 cement, you can achieve M50, 50 MP, 55 MP, even 60 MP also you can achieve. Okay, because it is not just cement which is there in the system. Aggregates are also there in the system, which are stone like masses, which also resist some uh, force loading action, which can also resist load. Okay, so we'll see how water to cement ratio, aggregate content, everything helps us to achieve strength. Okay, when we talk about OPC 43 grade, 43 means that it is the strength of cement. When we add water to cement along with fine aggregates, how much strength we'll get. Okay, so when we talk about the aggregates, they are inert material, they are not reacting, but they are still contributing towards strength. It is not like aggregate doesn't contribute to the strength. Okay, lime saturation factor is correct. It is 0.927, 0.92 to 0.93. For this question, the calculation, I will just write the answer here. So you can do the calculation later on and verify. So C3S content, it will be around 46.5%. C2S content will be around 25.39%. C3A content, you will get around 10.83%, and C4AF content will be around 9.21%. Okay, and lime saturation factor, it will come out to be 0.927. Okay, since it is less than 1, so we can say that the cement bag or the cement batch is suitable for use at. Okay, so now let's move ahead and try to understand what is happening inside cement and how it hydrates. Okay, so till now we know the composition of our Portland cement. Now we have three critical questions that we need to answer. Okay, first, why are certain compounds formed? Why C3S is forming? Why C2S is forming? Why C3A is forming? Okay, then why cement is reactive? Why? What is the reason which makes cement react with water? And then how cement reacts with water? Okay, so these three questions will answer these answering these three questions will clear all the major doubts that were asked recently. Okay, so to answer and understand them, we need to understand the microstructure of cement. Okay, so first we'll start with why certain compounds are formed. Okay, now we know that cement mainly has two phases, silicates and aluminates. So we saw C3S, C2S, and we saw C3A. Okay, and in this proportioning chart, we can see major proportion is occupied by these two phases, silicates and aluminates. Okay, so let's first talk about the silicates, C3S and C2S. Okay, so you can see when we talk about silicate structure, silica, it is in the form of uh, silica oxygen tetrahedra, CiO4 4 negative. This is the fundamental building block for all silicate minerals. Okay, and each tetrahedra, you can see it has one silica atom, which is covalented bonded by four oxygen atom. Okay, so and it has a free charge of -4. Okay, so in this tetrahedral structure, we see there is four unbalanced charges which are present right now. Okay, so the presence of these unbalanced charges, negative charges on the oxygen atom, they lead for the ability of silica to show linkage and polymerization through oxygen bond. So when we say that a system will be stable when all charges will be balanced. So what happens, this silica tetrahedra, it will also try to balance its unbalanced charges which is present on it, and because for this reason it shows linkage and polymerization. So multiple chains of silica, they will try to link with each other. Okay, so if this tetrahedra, so this single unit, it is known as tetrahedron. Okay, if this tetrahedra, they arrange in three-dimensional space in a periodic pattern, we get a crystalline material. Okay, so if this is arranged regularly in 3D, we'll get a crystalline material like quartz, which won't be reactive. Okay. However, if this silicate structure is not highly polymerized, it is not regular along all the three direction, it remains relatively isolated or moderately linked, not completely linked, then it will have some negative charge which are still unbalanced. Okay. And the presence of these unbalanced negative charge, they make silicate reactive and amorphous. Okay. So anything which is reactive, it is known as amorphous in nature, and anything which is not reactive, it is crystalline in nature. So when we talk about sand, okay, sand is also composed of silica. Okay, but it is not reactive because it has 3D structure of silicate. This silica tetrahedra, it is present in three-dimensional space. It is arranged in three-dimensional space. This polymerization is 3D in nature. That's why it is crystalline material. However, in cement, the silica tetrahedra, it is not 3D in nature. Okay, which makes it amorphous. There are still unbalanced charges that are present on the silicate mineral. Okay, which makes it reactive towards calcium. Okay, so if we try to understand what cement chemistry is, so how it is fundamentally controlled by the silica tetrahedra and its arrangement in its charges, then the next question that we need to understand is why C3s and C2s is formed. Okay, so we know that there are negative charges which are unbalanced on the silica tetrahedra. Now, these charges, they must be neutralized by some compound to form a stable phase. And in cement clinker, the calcium ions are there which balances these negative charges. Okay, so in belite, you can see there are two calcium ions which is giving us +4 charge, which balances the -4 charge which is present on the silica oxygen tetrahedra, and we this results in the formation of C2s. Okay, so you can see this is silica, these are four oxygen atoms, four negative charges, two are grouped with calcium, other two are grouped with calcium, and we get C2s. Okay, while in elite, there is three calcium ions which are giving us +6 charge, this silica which has -4 charge. Okay, and there is an additional -2 coming from oxygen ion. Okay, so that's why we form C3s. Okay, there are three calcium ions, there is silica and there is oxygen, so they combine to form C3s. Okay, now in this image you can see the layered crystal structure of C3s, okay, which is composed of alternating A and B cell. Okay, so you can see these red rods, these are oxide ions, O2 minus. This big yellow balls, these are orthosilicate ions, SiO4 4 negative, and these are calcium ions. Okay, so these uh, orthosilicate tetrahedra, they remain isolated and they are balanced by the calcium ions. You can see calcium ion is bonding towards two silica tetrahedra, this calcium ion is bonding with two silica tetrahedra, this calcium ion is bonding with two silica tetrahedra. There's oxygen in between to balance the remaining unbalanced negative charges from calcium ions, and this gives rise to subshell type A. Then there's type B also, where there's no oxygen present, there is just silica and calcium present. So like this, the structure of calcium elite is a little complex. Okay, it is not very oriented, it is distorted and it is imperfect in nature. Okay, there are multiple sides which are amorphous in nature. Okay, and they have poor packing also at the structural level, which makes C3s unstable, and that's why it is formed at very high temperature, and that's why it is more reactive towards water, because it is still unstable. Okay, it is not perfectly balanced, it is not perfectly oriented, it has multiple orientation, multiple structures which are present in its nature, and it makes a it is the reason why it is formed at very high temperature and why it is very reactive towards water. While if you see the image of C2s, where each silica tetrahedra is only surrounded by two calcium ions, which is sufficient to satisfy the charges. You can see this is silica tetrahedra, this is oxygen bonds of that tetrahedra of that silicate atom, and you can see there is calcium which is present, which is bonding towards 2 oxygen of each tetrahedra. Okay, so compared to C3S, this arrangement leads to better packing efficiency because all bonds are clearly defined in C2S. And that's why C2S it forms at lower temperature rather than higher temperature because it has more stable structure compared to C3S. And that's why it is less reactive also because it has more stable structure. So more stable is the structure is less reactive it will be. Since C3S is more distorted, complex in nature, it is more reactive also. And that's why it forms at higher temperature also. Whereas C2S being more oriented and more stabler compared to C3A, it is less reactive and it forms at lower temperature. Okay, and that's why it contributes to long-term strength and not early strength. Okay. Now, if we see aluminates, that was silicates. So, if we see aluminates,
So if we see aluminum,
aluminum oxygen
aluminum,
AlO4 5 negative. So, like silicates, aluminum also has tetrahedral units. However, in case of aluminates, there are five unbalanced charges, whereas in silicates,
charges,
there are
whereas
four unbalanced charges.
four
And
unbalanced.
in this, we have
And
aluminate
in this, we
again
have
at the
aluminum.
center of the tetrahedra surrounded by four oxygen atoms, and there are five unbalanced charges present. To balance these unbalanced charges, we have calcium ions. Okay, so these calcium ions they balance the unbalanced charges, and how it balances it balances in the form of making a ring kind of structure. So you can see this is aluminium pink one, and this is oxygen bonded with aluminium, and they form a ring kind of unit, and the unbalanced charges on the oxygen it is balanced by the calcium ions. Okay, so the structure is built with calcium ions and rings of 6 alumina tetrahedra which forms this unit. Okay, however, unlike silicate, aluminates don't exhibit any polymorphism, so it is not oriented towards for a longer time. So here we talked in the initial slide now, like due to unbalanced charges silica show polymorphism, but here there is no polymorphism. Why? Because it's enclosed in the form of rings. Okay, so since it is enclosed in the form of rings, it doesn't extend to larger distance, it doesn't form polymers, and that's why since it doesn't it doesn't show polymorphism, it has simple cubic structure. Okay, so this ring you can see it is kind of a cube only, and this simple cubic structure and less polymorphism is the reason why C3A is more reactive compared to C2S and C3S. So more is the polymorphism, more is the crystallinity in the system, lower will be the reactivity of the system. Lower is the polymorphism, more is the reactivity of the system because more is the amorphousness in the system. Okay, so that is the difference between aluminates and silicates, and in silicates also between C3S and C2S. Okay, is everyone clear with this form of atomic structure and how it is oriented? I'll just suggest you to just listen to this lecture once again so that you get more clarity about what I have spoken. Any doubt in this part? Yeah, this PDF will be available to you. Polymorphism means linkage of each unit. So you can see here, this is one tetrahedra, one silica tetrahedra, one unit of SiO4 minus, SiO4 4 negative. Now to balance this 4 negative charge, what will happen? This oxygen it will link to other some other silica also. Then there will be oxygens of that silica, like you can see here. This oxygen it linked with one another tetrahedra unit. Then this oxygen it will link to one other silica, then this oxygen to one silica, this oxygen to one silica. So this linkage of each single units, this is known as polymorphism. The role of gypsum we'll understand slowly when we'll talk about hydration of cement. See, when we talk about composition, we have given the range. It is not like very specific 50%, 40%, 30%. There is range in which cement composition can vary. Okay, so that's why you can see like someone will have, if suppose C3S content should be in the range of 40 to 60%. Some cement company will manufacture cement which has C3S at 58%. Some will manufacture cement which has C3S as 44%. So that's why from company to company difference can come, and that's why grade difference also comes. F is for Fe2O3 in that equation and that question? Polymorphism will reduce the reactivity. Why sand is also made of silica, but it is inert material, it doesn't react with water. Why? Because of 3D polymerization that is present in sand. Sand has silicate structure which has polymerization in 3D network, okay, which makes it very less reactive. And when something is not reactive, we call it as crystalline in nature. Crystal means which has perfect structure, okay, perfect polymorphism in 3D. Okay, that is a crystalline material. And amorphous material is something which has unbalanced charges, which has ability to react. Okay, cement has ability to react, while sand doesn't has ability to react. Okay, now this was the first question. Okay, now we know that how certain phases are formed, why certain phases are formed, why C3s is forming, why C2s is forming, why C3 is forming. Okay, but why are they reactive? Why cement is reactive? That is the second question that we need to answer. So, if you see, one common feature in all cement mineral is that it has large anions bonded with small cation. So, we have SiO4 4 negative units or AlO4 5 negative units which are bounded to Ca plus 2 anions. Okay, so they are large anions. This is very small cation. So if we see the atomic size, it will have a very high size. It will have a very comparatively very smaller size. Okay, so due to this large anion, if we just see a simple cubic structure, okay, so what will happen if we see these anions? They are occupying the corner positions of a cubic unit. So what will happen due to the presence of larger size? They will hinder the packing of each other. They won't allow the anions to pack close to each other. Okay, so since they don't have very good packing efficiency because of their larger size, the packing efficiency of the compound which is found finally, it won't come in the required range of stability. So form a very stable compound, we need packing efficiency of 0.64 to 0.74. Okay, and due to the presence of large size anions, the packing efficiency is lower than this. Okay, packing factor is lower than this, and this is why cement becomes reactive. Okay, how cement improve its packing efficiency? To achieve this efficiency, what happens? These unstable cement compounds, they incorporate water of crystallization. So cement, it reacts with water, okay, within its structure to fill the spaces which is left over between cations. Okay, and this reaction of cement with water and this incorporation of water of crystallization is something what is known as hydration product, and this reaction is known as hydration reaction. So the main reason is to improve the packing efficiency. Right now, due to the presence of large anions and small cations, there are a lot of spaces which are left within a unit cell which is not occupied, which is reducing the packing efficiency. And to improve on that efficiency, cement reacts with water to form hydration products. Okay, it is the entire unit C3s, C2s, they all are not like stable phases. They have very low packing efficiency, and that lower packing efficiency make them reactive towards water because they want to achieve stability. Every atom, everything, always they want to achieve the lowest energy state, and lowest energy state will be achieved when they will have the best packing efficiency. Okay, so to achieve that state, cement reacts with water. Okay, its amorphousness, it decreases when it reacts with water to form a stable compound. So now we have seen that why certain phases are formed and why those phases are reactive towards water. So next thing that will be there in our story will be how cement and binder material they react and how this hydration reaction happens. Okay, so first we'll see hydration of silicates. So when we talk about silicates, we have C3S and C2S. When it reacts with water, it produces calcium silica hydrate and calcium hydroxide. So you can see here both the reaction. C3S, it reacts with water to form CSH and CH. To 2 moles of C3S, it combines with 6 moles of water to form 1 mole of CSH and 3 moles of CH. So in terms of quantity, if we see 100 grams of C3S, it requires 24 grams of water to produce 75 grams of CSH and 49 grams of CH. Whereas belite C2S, 2 moles of C2S, it reacts with 4 moles of water to form CSH and CH. So 100 grams of C2S, it will require 21 grams of water to produce 99 grams of CSH and 22 grams of CH. So we can see here there are two hydration products which are forming, CSH and CH. So CSH, calcium silica hydrate, is the main strength bearing compound in cement paste and in turn concrete. So when we talk about strength of concrete, how cement contribute towards the strength of concrete, it is due to the formation of CSH. The more is the quantity of CSH in this concrete, the higher will be the strength of concrete. Okay, now why this is written as C dot dash S dash H and why not as CSH? It is because this structure, calcium silica hydrate, it doesn't have very well defined composition. The Ca to Si ratio in calcium silica hydrate, it can vary from zero point 0.1, 1.5 to 2 or 2.5%. Okay, since it is not very well defined and it is poorly crystalline in nature and porous solid, which exhibits like gel like property, that's why it is represented with dash and not directly written as CSH. Okay, while CH, it is also known as Portlandite. Okay, so CH is nothing but CaOH whole twice. It is known as Portlandite, which is precipitated out of pores in concrete. So when we talk about concrete, there are pores present in concrete. Okay, in these pores we'll find CH, which is leached out. Okay, this is an unwanted product in concrete. The product that we want for strength is CSH. CH is something which is unwanted. Okay, and it is present in the spores phase in concrete, and it is why it is unwanted product, because it is the one which will give rise to durability issues later on. Okay, so later on when we'll talk about durability problems, we'll see this CH is the problem. Okay, we don't want CH in concrete. Okay, lower is the content, CH content in concrete, better will be the concrete. Better will be the concrete. Okay. Now, in case of hydration aluminates, we have just studied that C3 is very reactive due to its lack of polymerization and open cubic structure. So, reaction with of C3A with water is very volatile in nature because it is highly reactive and it leads to immediate stiffening of cement paste. Okay, so when we add water to C3 cement, the first product, the first composition of cement which reacts with water is the C3A. Okay, and it causes stiffening. Okay, it will make the cement paste very stiff. Okay, which is also known as flesh setting. How it happens? So the C3A combines with water to form C3AH, calcium alumina hydrate. Okay, so 100 grams of C3, it combines with 40 grams of water to form 140 grams of calcium alumina hydrate. And this calcium alumina hydrate, it gives rise to flesh setting. So you will see, as soon as I will add water in cement, there will be instantaneously it will set, it will start to set. And why it is a problem? Because when we talk about concreting, we are mixing concrete at a certain location and we are pouring concrete to at a certain different location. So there are cases when we need to transport the concrete also from one place to another. If my concrete will set instantaneously, then how this transportation will be a problem. If it is already set, then we won't be able to pour it into big molds, and it won't be able to flow and cover the entire space inside mold into to form a definite shape that we want. Okay, so that's why we don't want flesh setting to happen in concrete. It should remain workable for some time, and then after 24 hours or after one day it should start to set and gain shape. We need concrete, it should, we want that concrete to be workable until we have transported it to site and we have poured it inside the foam works. Okay, and that's why this flesh setting becomes an issue. So presence of C3, it is undesirable because it is not contributing towards strength. We can't see the formation of CSH that is happening. It causes premature stiffening of cement paste, which makes cement less workable because of flash setting. And in hardened concrete, it is susceptible to degradation to sulfate attack. This we will see later on. Okay. However, even knowing that C3 is a problem, why C3 is present in cement composition? Because it acts as a flux and it reduces temperature burning of clinker. So when we talk about clinker production in kiln phase, the presence of C3A, it reduces the temperature required to form C3S. Okay, that 1500-degree mark. If there is no C3A, we need to increase this temperature maybe to 1700, 1800 degrees Celsius also to combine lime and silica. Okay, so that's why we say C3A act as a flux. Another positive point of C3A is it bind chlorides. So over time in this course, we'll understand that chlorides are the major source of corrosion in reinforced concrete. So what happens? C3A, if it is present, it has the ability to bind chlorides when they ingress through concrete. Okay, so that's why C3 is also is again important to us. Now, how can we prevent this problem of flash setting? To prevent this problem of flash setting to occur in concrete and to make concrete pumpable and flowable for a certain period of time, we add gypsum to cement at the end of clinker production stage. So what happens when we add gypsum? So gypsum, if gypsum is present in cement, it reacts with C3 and water to form ettringite, which is more stable and slow forming compound. So what will happen if there is no gypsum? C3A is reacting with water to form calcium silica, calcium alumina hydrate. But if there is gypsum present, then what will happen? C3A will react with gypsum in the presence of water to form ettringite, and this is slow forming compound. It won't form instantaneously, it will take time to form. If it will take time to form, it will consume water slowly. If water is consumed slowly, there is more water available to give concrete the flowability that we need. Okay, so what gypsum does, it delays the stiffening process, it prevents the flash setting, and it allows the cement to remain workable for a longer period of time. However, as hydration continues, what will happen? Gypsum will get consumed. Okay, once gypsum is consumed, and if there is still C3A present in the system, then what will happen? This ettringite that was formed due to reaction of C3A and gypsum, it will react with the remaining C3A to form monosulfates. Okay, so ettringite, it converts into monosulfate. Okay, it is again calcium silica sulfo hydrate, but with a different composition. Okay, so this conversion of ettringite to monosulfate, it involves reduction in volume. So suppose its volume was 1 meter cube, the volume of monosulfate will be around 900.9 meter cube, zero point 0.8 meter cube. So there is reduction in volume that is happening due to this reaction, which can lead to some shrinkage problem. Okay, but the important thing is this reaction is delayed now, which was causing flash setting in cement. Okay, it is delayed due to the presence of gypsum. Okay, and this reaction, it happens later on, not in the early stages. Okay, now in hardened concrete, suppose I have monosulfates present. So what happens if sulfate sulf if they from external sources, if sulfate ion comes inside concrete, what will happen? This monosulfate can again convert back to ettringite, which will bring involve expansive reactions. Since ettringite to monosulfate conversion led to volume reduction, monosulfate to ettringite conversion will bring volume expansion in nature. Okay, in picture. Okay, so for if we have a hardened concrete and there is volume expansion happening inside, then it will give rise to cracking in concrete. Okay, which is not desirable. So this is known as sulfate attack. Okay, later on we'll see in the course this part that we have talked right now. It is known as sulfate attack. Okay, which is a durability issue for concrete. So in week 10 or week 9 content, we will talk about, we will again touch upon this point. Okay, what is sulfate attack? Okay, it is the conversion of monosulfates into ettringite in hardened concrete state. Okay, which gives volume expansion and damages the concrete. Okay. Now, based on this understanding of hydration of alumina, hydration of silicates, just try to answer these two questions. And in the meantime, if you have any doubt regarding hydration of cement, you can ask. You will get the recording of the session. Don't worry. Just answer these two questions right now. What is the difference between flash setting and false setting? So you might have heard a term known as false setting also occasionally. What is the difference between the two? And also think about the second question. From durability point of view, which clinker phase is important? C3S or C2S? So I have shown you the hydration products which are forming. So think about that reaction in the products which are forming and tell me the answer for this question. Can anyone tell me the answer for the first question? What is the difference between flash set and false set? What do you mean by flash setting? Tell me that first. You can unmute and speak also if anyone wants to. If you remember, initially during cement production, we we said that clinker is first cooled and then it is blended with gypsum to form cement. Blended and grinded with gypsum to form cement. Just think about that part. Why clinker is cooled before addition of gypsum? Flash setting, we know it is quick setting. Why? Because calcium C3A it reacts with water to form CaH, calcium alumina hydrate. Now this reaction it consumes a lot of water immediately. So suppose you have added 100 grams of water in. Suppose you have added 1 kg water during concreting. There is no gypsum present. Okay, in cement. So what will happen? C3A present in cement, it will consume a lot of water. Up from 1 kg support, it consumes 500 grams of cement water to form calcium alumina hydrate. So if there is very low water present in the system, my concrete won't be workable. It will appear to have set. Okay, for workability, for flowability of concrete, I need water which is free, which is unreacted. Okay, that will bring the workability to the system. And flash setting means that there is not enough water present in the system to make concrete flowable or workable. Okay, that problems comes when C3A reacts with water to form CaH. Okay, which is very instantaneous and very immediate and which consumes a lot of water. Now, false setting is, so suppose if I don't cool down clinker, what will happen? CaSO4 dot 2H2O, the gypsum that I'm adding, okay, it will, due to the presence of heat, it will convert into CaSO4 dot half H2O, which is known as hemihydrate, and it will release some water. Okay, now what happens? This hemihydrate, okay, this hemihydrate is there in my cement. Okay, Now when I add water to cement, okay, what will happen? This hemihydrate, it will first convert into gypsum, CSO4 dot 2H2O. Okay, and since this reaction will consume a little bit water, it will appear that the cement paste has set. Okay, and this is known as false setting, conversion of hemihydrate into gypsum when water is added to cement. Why it is known as false setting? Because when we mix if we again do remixing of cement, okay, without addition of water, then this gypsum, it will again break into hemihydrate and water. Okay, so water, it is like, it will appear to be set, but upon remixing it will again become free. So that's why it is known as false setting. And false setting comes because hemihydrate converts into gypsum. And that's why we say that before addition of gypsum to clinker, clinker needs to be cooled down so that this reaction doesn't occur. Okay, this is known as false setting. Everyone clear with the concept of false setting? Okay. Second question, from durability point of view, which clinker phase is more important? So just I will just copy the two equations for you. This is the hydration of C3S, and this is the hydration of C2S. Okay. So if you remember, we talked about two hydration products, CSH and CH. Which of them is undesirable to us? CH or CSH? Okay, CH is undesirable to us. So if there is more formation of CH, then there is more chances that later on CH will make give rise to durability issue. So a clinker phase, for clinker phase from durability point of view, C2S is more important because it produces less CH content per 100 grams of C2S. So you can see, compared to C3S, almost half CH is produced due to C2S for the same amount of phase. Okay, so that's why I say from durability point of view, C2S is more important. However, from strength point of view, C3S is more important for early strength gain. Why? Because C3S reacts readily. Okay, while C2S, it takes time to react. So if we want early strength, we need more proportion of C3S in a cement. What is the temperature of fresh cement paste and what is the acceptable temperature range? Generally, we say that the temperature should be lower than 40-50 degrees Celsius only, because once the temperature goes above 70 degrees Celsius, then there are certain phase changes that starts to happen inside the cement. Okay, so that's why we do curing. Why we do curing? So that there's no evaporation of water from the cement paste system, and there's that temperature regime is maintained. Okay, there is no heating of the system. That's why curing is so important initially when we talk about concreting or cement paste. Okay, above 70 degrees Celsius, it is not desirable because then ettringite starts to convert into monosulfates. It shows some conversion behavior. These all things we'll start to understand when we will go later on week 2 and week 3 content. Okay, when we talk more about cement hydration or types of cement, what is happening with cement, why we talk about cold weather concreting, hot weather concreting, these things will come up into picture. Okay. Okay, so these are the answer for these two questions. Okay, now knowing about cement hydration, let's just see a flowchart that describes the process, how it is actually happening on a larger scale. So right now we have seen everything from microstructure point of view. What about on a larger scale, how it is happening? So when we talk about cement hydration, it is a surface phenomena. So this is my cement grain, this is water. Hydration, it starts from the surface of cement. Okay, so cement, when it comes in contact with water, hydration reaction happens at the surface, and hydration product forms at the surface of cement grain. Okay, now which hydration product I am talking about? I am talking about CSH gel. So this CSH gel, it will form on the surface of cement grain, and it will produce a semi-permeable membrane for water. So inside I have unreacted cement which is present, but there is a membrane of CSH that has formed over the this cement grain, okay, which will act as a barrier for interaction of water with the unreacted cement inside. Okay, now what happens? This gives rise to osmotic pressure. So we have a large concentration of solute is higher inside the cement grain compared to the concentration of solute which is outside the cement grain. So unreacted cement, it is very high inside and very low outside, and water, it is high outside and low inside. So there is concentration gradient that has been developed due to this layer of semi-permeable membrane that has formed over the cement grain. Now once this pressure rises above a critical limit, what happens? They will break the membrane. Once the membrane is broken, what happens? Water meets the unhydrated portion inside, while the unhydrated cement, it tries to move outside, and there is hydration of cement grain, and there is void between the cement grain also starts to fill up as hydration happens outside also. Okay, so when two cement grain, they start to merge together due to hydration, we say that setting has started. Okay, that is known as solidification or setting occurs because of lack of water. Now the water is occupied by hydrated cement grains, and as the cement, and as this system of cement paste, it becomes closely packed due to hydration, we say that hardening has occurred. Okay, so setting occurs when multiple grains, they merge with each other due to hydration, and hardening occurs when the system becomes closely packed, okay, where it is able to take strength, bear a lot of load. Okay, so this is the process. From surface, hydration starts, then osmotic pressure rises, then the this semi-permeable membrane that is formed on the surface, it breaks, water moves inside, certain phases, they start to move outside, they dissolve in the system, hydration deepens inside. Okay, and there is binding of different cement grains, it starts to happen, and then the binding of entire system happens. Okay, so when hydration occurs, we see there are different hydration products which are formed. CSH, ettringite, then there is calcium hydroxide, then there is monosulfates. Okay, so this is a little bit out of course, but I just want to show you at microstructure level after hydration how uh, these hydration product they appear. So in this image, you have four different kinds of products that you can see. So this is like a scanning microscope, SCM image, scanning electron microscope image of a 7 day old had hardened cement paste, and this is at a magnification of 3500. Okay, there are different cement hydration phases that are present in this image. So can anyone tell me if you have any idea about how CSH will look, how ettringite will look, how CH will look, and how AFM will look under microscope? Any guesses? This is just an additional learning. I guess it was not the part of the session that you have seen, but just to tell you, if we see a cement paste in microstructure, how we'll see the paste. Any idea? You can make guesses if you want. Okay, I will just tell you the answer for this because I don't think so it will be clear for you to answer. So you see this um, at the bottom list, this gelatinous material that is present here. This is CSH. Okay, and these needles that you see around CSH. Where is my mouse? Just a second. Okay, this is CSH, and these needle kind of things that you are seeing here, these are known as, these are ettringites. Okay, the plate like structure that you see here, these are all AFM. Okay, monosulfo aluminates, and these crystalline kind of things that you see here, these are all calcium hydroxide. Okay, so when we, on microscopic level, when we see cement hydration, we can identify different hydration phases like this. Okay. Okay, this is how we can judge. Okay, you can read more about this, but I just wanted to give you a basic of what is SCM and how cement paste appears in SCM. Okay, so till now we talked about cement hydration. The next is the kinetics of hydration. Like by kinetics, we mean at what rate hydration occurs. Okay, so when we talk about hydration kinetics, it involves four stages. Okay, there is pre-induction period, that is first few minutes, where there is rapid dissolution of ionic species like sodium, potassium, and sulfates. C38 starts to dissolve and react with gypsum to form ettringite, and there is a little bit CSH formation that also happens on the grains of C3A. So this is pre-induction period. Okay, then there is dormant period. Okay, where early hydration, this early rapid hydration, it slows down due to deposition of CSH layer on the cement grain. Okay, and which gives rise to the semi-permeable membrane that we talked about. Then there is acceleration period where there is rise in osmotic pressure which breaks this semi-permeable layer, and there is nucleation and growth of CSH and CH which occurs. And now in with C3S, C2S also starts to hydrate, and then there is post acceleration period where C3S hydration has almost completed, but C2S hydration, it gains speed. Okay, so there is more contribution to C2 of C2S and CSH formation. And if gypsum is consumed, then we'll see that ettringite, it starts to convert into monosulfate as gypsum quantity, it starts to decrease. Okay, so this is how there are four different periods in hydration of cement. Okay, so suppose I have different hydration phases, C2S, C3S, C3A, and C4AF, and I give you this chart. Okay, dormant period, acceleration stage, and post acceleration stage. So, can anyone tell me what this these four curves will represent? What will be, what is this curve representing? Which phase it will represent? Which phase the second curve will represent? Which phase the third curve will represent? And which phase the fourth curve will represent based on time, hydration time. So at zero in cement, I added water, and there are four lines. Each of these lines, they define one phase of cement. Can anyone identify what is one, what is two, what is three, and what is four? So this first curve, what will be this first curve representing? Which phase? C3S, C2S, C3A, or C4AF? So you can see the reaction of this first curve, it is starting just after 1 hour mark, and then it is growing in the acceleration state, and then it is slowing down in the post acceleration state. So which what can be this? Okay, so this will be C3s. So we have seen C3s it starts to show reaction at the end of dormant period. Okay, so this you can say as pre-induction period also, dormant period also. In the acceleration state, we know that C3s it starts to convert into CSH as the osmotic layer pressure rises and the semi-permeable membrane it breaks, and over time it slows down. Okay, now this curve 2, if you see this curve 2 is it is something that has shown reaction from the start. Okay, and then it remains constant, and then again it increases later on. So this will be C3a. So initially C3a it will react with gypsum in the presence of water to form ettringite, and then over time as gypsum will be consumed, C3a it will convert into ettringite will convert into monosulfate. So that's why the reaction again shoots. Okay, as C3A reacts with ettringite to form monosulfate. Then this curve 3 that you see, okay, the curve 3 initial reaction was shown, and then it becomes stable, again it increases a little and becomes stable, that will be C4AF. So just like C3A, hydration for C4AF also occurs. And the fourth curve which shows the reaction at very later ages, that will be C2S. So we know C2S it is slow reacting species, so it shows reaction at very later ages. Okay, now this question, here again we have four curves, but these four curves they are representing CSH, CH, AFT and AFM phase. So can anyone label me 1, 2, 3, 4 now, based on the hydration product which are formed at different ages? Second is C2S, second is C3A, fourth is C2S. Just label this question number 11 fast. What will be this first curve? You can see the reaction product formed from the start, it became stable later on. Okay, it formed in a very small quantity initially, and then over time it starts to grow a lot. Okay, after hardening period you can see it is shooting. Okay, so what it will be? Yes, it will be CSH. Okay, second one, you can see initially it formed, it grew over time, and then it declined in hardened period. So it is, yes, it is AFT. Okay, ettringite it starts to convert into monosulfate, so the quantity of ettringite it starts to drop as monosulfate formation increases. Okay, third one, you can see initially it was not there, however in the setting period it starts to grow, and then it grows steadily. As CSH is increasing, this is also increasing. So third one is CH. Okay, Portlandite. As CSH increase, it also increase. But the rate here was more, and then it slowed down because here now C2S contribution is more, and C2S produces less CH. That's why here the curve is flatter compared to initial age. And the fourth one will be AFM, more ettringite. As ettringite, AFM monosulfate. At ettringite starts to decline, monosulfate will start to rise. Okay, so this curve should be like this. From here it should be like this, it should increase like this. Okay, clear with the hydration from oxide compound composition, how they are changing over time, and the final hydration product, how they are changing over time. Just answer this one more question. What is the order of reactivity? I have C2S, C3S, C3, and C4AF. So if I want to rank them in terms of reactivity, which is the most reactive and which is the least reactive? Very simple question. Okay, C3 is the most reactive. And which one is the least reactive? C2S will be the least reactive. Okay, so these simple questions, they are generally asked in your assignment, and to have better clarity you can revise these two questions. That will completely clear your kinetics of hydration. Okay, these two diagrams, they will give you the all the clarity that you need for these four periods that we discussed here. Okay, now, let's move towards the final segment for today's discussion, and that is about two important properties of cement hydration, which are heat of hydration and degree of hydration. Why these two properties are important? Because they are the things that actually matter to us from application point of view. These terms help us to choose among various types of cement for a application purpose. Okay, so first we have heat degree of hydration. So degree of hydration is the measure of how much water has reacted with cement. Okay. So it is the fraction of cement mass hydrated at any time. Okay. Now we know cement hydration is a long process. It continues for a long period. That's why we can see in the first figure. Okay. How hydration after the initial steep rise, it continues to increase steadily at a steady space till 28 days. Okay, so this is the degree of hydration is amount of water that is consumed by the system. Initially it is very high, and then it slows down, and then it slowly hydration continues. Okay, so at 28 days we generally say that more than 99% of hydration that should have happened will happen. However, this statement is not true in case of when we add mineral admixture to the system. Why? We'll see later on when this topic will come up around in week 3 or week 4 content, that mineral admixture, they start to hydrate when CH is produced by OPC. So the CH that is produced by OPC, it is consumed by mineral admixture to form CSH. Okay, so this CH production, it takes time, and then consumption will be done by mineral admixture, and then CSH will form. So instead of reaching 99, 90 to 100% hydration limit at 20 days, for mineral admixture, hydration can grow up till 120 days also. Okay, so this is degree of hydration. Now in the second figure, you can see the volume of fraction of unhydrated and hydrated cement after different time. So at 0 hour, you see there is capillary water, that is free water, and then there is cement which is unreacted. Okay, after zero point 0.4 hour, you can see the water content decreased. Okay, there is gel water. Gel water is something which is reacted water, which is present between cement hydration product. There is gel solid, which is my hydration product, CSH, and there is unreacted cement, which is now decreased in proportion. Then again, over time, you see water again decreases. Okay, there is more amount of gel water in the system, the water that is trapped between CSH gel. There is more CHH formation that has occurred, and there is lower quantity of unreacted cement that is there in the system. So this is known as hydration. Okay, and the amount of water that is still unreacted, or the amount of water that has been reacted, it defines the degree of hydration of the system. After degree of hydration, we have heat of hydration. So when we talk about cement hydration, we should remember that cement hydration is an exothermic reaction. It liberates heat when cement water is added to cement. As hydration occurs, heat is liberated from the system. So The amount of heat released by a clinker phase upon reacting with cement is known as heat of hydration. Okay. Now, since heat is released during hydration, we can say higher is the heat of hydration, quicker is the reaction. Okay, so as more cement will react, more heat will be produced. So higher is the heat of reaction, quicker is the reaction because more cement is reacting. And that's why when we say about finer cement has more surface area, so it can react with more amount of water, so it will have higher heat of hydration also. More exothermic reaction will also occur in fine grains. Okay. Now, different clinker phases, they have different heat of hydration. Okay. C3A has the maximum heat of hydration. Then C3S has the second position is the at the second position. Then we have C4AF, and the least heat of hydration is of C2S. Why? Because C2S is stable compared to C3S and C3A. So it takes times for C2S to react with water, and that's why the heat of hydration is also lower because it reacts slowly with water. While C3A, it reacts rapidly with water, and that's why heat of hydration is also high in case of C3A. So in this figure, you can see at different cement hydration stages how heat is evolving. So this was the curve of hydration kinetics that we saw earlier. Okay. So initially, there is a heat burst. Okay. In the pre-induction period, because of ionic movement and flesh setting chances that can occur, which a little bit flesh setting or a little bit reaction of C3A with water that will occur, that will give rise to initial heat burst. Then in the dormant period, you will see that the heat of hydration reduces to very low value because of the formation of CSH cover on the cement grain. And as osmotic pressure rises, okay, it breaks the CSH cover, and again the heat of hydration increases because CSH formation starts to happen. Okay, then again this will slow down because now C2S is governing the hydration, and C3S anhydrous C3S content reduces, which reduces the heat of hydration again. And then over time it slows down as the unreacted cement becomes lower and lower. Okay. And cumulative plot is like this. Initially there is a small increase, then there is a large increase as setting and hydration occurs, and then there is slow strength gain which defines the hardening period. Okay. Now, after now knowing the clinker composition, we know how much C3 is there, how much C2S is there, how much C4AF is there, how much C3 is there. We can calculate the total heat of hydration. Okay. How? If we know this proportion and we know how much heat of hydration a certain phase requires per gram of that proportion, we can calculate the heat of hydration. So this heat of hydration, it is given to us in terms of joule per gram. So this is joule per gram, and this we will know in terms of gram. So in 100 grams of cement, based on the percentage of each proportion, we can calculate how much gram will be each proportion. Okay, so from that we can calculate the total heat of hydration of a cement. Okay, assuming that cement has reacted 100%, there is 100% hydration. Okay, so just give it a try. You know the heat of hydration of each phase, and you know the percentage of each phase. Okay, so what will be the heat of hydration in terms of joule per gram? So I have 1 gram of cement. What will be the heat of hydration for this 1 gram of cement composition? Can you even do this calculation? I got the report for heat of hydration by kilometer mentions that the heat of hydration is 6. Yes. 367 kilojoule per kg at 7 days of concrete. How it is lower compared to the data you have shown? I have not shown any data for concrete heat of hydration. I'm just sharing you the data for certain different phases. Okay, how much C3S has heat of hydration per gram. Now this you're talking about say 367 kilojoule per kg of concrete. So in 1 kg of concrete, what is the proportion of cement? Okay, in that cement, suppose per kg you had around 300 grams of cement. So in that 300 gram of cement, you need to check how much will be the proportion of C3S, C2S, C3 and C4AF. Now from that proportion, multiply that proportion with these values and then calculate the total heat of hydration of the system. Just do that as an exercise and try to compare what is the value that you got in the report and what is the value coming from this. So this data that I have taken here, it is just a rough data that I have taken from one of the research paper that you can find online anywhere. Okay, this value is not very accurate, they can vary, but it was just to represent the trend that C3 is has more heat of hydration than C3S, then C2S and then C4F. Okay, just take it as an exercise, not as the exact value. This is the last slide that we'll discuss. Okay, I had more slides regarding water and pores inside cement paste, but that will take in the next session, because based on that I have numerical also, which is very important for the course. So that will take in the next session. We will start the next session by discussing about water and porosity in cement paste. Okay, so just solve this question and then I will end the session and I will make myself available for any further doubts if there are. Did anyone do the calculation? So total heat of hydration, it will be zero point 0.5 into 502 plus zero point 0.3 into 260 plus 0.12 into 867 plus 0.08 times 419. So it will come out to be 466.56 joule per gram. Okay, so when we vary the proportion of cement, like next session or next to next session, you will talk about different types of cement. So when we'll talk about different types of cement, you will see that these proportions are varying. When the proportion will vary, you can see that the total heat of hydration liberated by different system cement system will also vary. So when we talk about high weather concreting, hot weather concreting, we want cement which has lower heat of hydration. So we can judge from the composition. In cold weather concreting, we want a cement which has higher heat of hydration. Okay, so we can judge from the composition. So early strength grain concrete, we have different weather, according to different weather, according to different need, the heat of hydration can change, so that we can judge from this calculation. Okay, so this was all for today. The remaining part, like water within the cement paste and porosity, will take up in the next session, at the start of the next session. Okay, thank you.